Okay, let me start. So on Wednesday, I've introduced so-called matrix calculus. But to be honest, okay, theoretically, nothing is new because it's really building a point on the multivariate calculus that we have developed in calculus 3. But then the crucial difference is we try to develop a technique that you can compute the differential or the gradient of a matrix value function or a function whose domain is the space of matrix without spelling out the coordinate. And we've seen, okay, last time we've derived the formula for the so-called maximum likelihood estimator by using matrix calculus in a quite clean manner. And to finish this course, okay, I'm going to give you a new proof to our old result. So this is a result that we encountered a few weeks ago when we studied S3D, and that is the low-rank approximation theorem. So what is the low-rank approximation theorem? We try to approximate a matrix by another matrix of strictly lower rank. So let me formulate that more accurately. So suppose you're given a matrix A, and now I want to approximate A by a matrix of the same size but a strictly lower rank. So let me fix R, which is an integer less than or equal to the rank of A. Then what I'm going to do is to find a B of rank R such that it's as close as A as possible. But how do we measure the distance between two matrices? The way to do it is to use the so-called Frobenius law, so such that this term is minimized. And then a few weeks ago, I do it by using a very elementary but very clever result by von Neumann, the von Neumann trace inequality. And this time, I give you a new proof by using essentially calculus. But to do that, I'm going to do a little reduction. The reduction is the following. So I want to find a matrix B of rank R. So it turns out every matrix of rank R can be decomposed into a product of X times Z transpose. And X and Z, they are matrices of size M times R and N times R respectively. Like at first, when you look at that, it may look mysterious, but think about it, this is how you construct rank 1 matrices. I can give you a sketch proof, why you can do it. So, let we look at the row space of B. The row space of B is spanned by, let's say, because this is rank R, so if you want to span the row space, you just need R column factor. So set 1, set 2, up to set R. Okay. So this is rank R, so I just need R factors to span the row space. And then now, because set 1 to set R span the row space, so as a result, every row of B, or let's say the ith row of B, the ith row of B can be written as a linear combination of this set I, set 1 up to set R. So you can write it as a linear combination of the set J from 1 to R, and then there are some coefficient in the flange, Xij. Then you're essentially done, Then now check this relation would imply B equal X times Z, and of course X is the matrix formed by all these Xij, and Z is given by these column vectors. Sorry, it's a bit small. Let me make it larger. So this is not a difficult procedure, It's just to analyze the row space of the given matrix B, but because this is a rank R, so I can span it by using R column vectors. You write all the rows of B one by one as a linear combination of this set 1 to set R, then I create this factorization. Oh, sorry, transpose. Forget. ごめんなさい啊。Okay. So every rank out matrix can be factorized as a product of two matrices, x times z transpose, and then x and z has the appropriate size, okay? But then the size is to control the rank of these two matrices. But I'm going to impose an additional condition just for convenience, okay? Otherwise, there's no uniqueness in the choice of x and z. So the additional hypothesis that I'm going to impose is that I want to choose an orthonormal basis, okay? So I can choose an orthonormal basis here. Or equivalently, okay, if I choose the columns of Z to be orthonormal basis, that means that Z, this matrix, will satisfy a condition that Z transpose Z equal to identity. Now be careful, it does not mean Z is orthogonal because Z is not a square matrix, okay? So Z is not orthogonal because Z is not a square matrix. But Z transpose Z equals to identity just means I require the columns of Z to be orthonormal, okay, to be more precise, to be orthonormal. So as a result, okay, after I impose this additional condition, I kind of, it turns out, okay, it will make this factorization unique, okay? But then I can't tell you why this factorization is unique now. You will figure that out later. Essentially unique, okay? Let me put it that way, sorry. Okay. So, in other words, I'm trying to transform my optimization problem. So initially, I try to minimize A minus B such that the rank of B is R. So now, because I can replace a rank R matrix by X times Z transpose, so I'm really just minimizing, okay, this term over here. I'm putting a constant in the front just for convenience later, okay? So I put 1 over 2, not for educated reason. It just, okay, simplify the derivatives later. But there's a constraint, okay? The condition is that the set is not random. The set would, the columns would be orthonormal, or equivalently, set transpose set is identity. So this is constraint optimization problem. I have that word there. Okay. So we have an objective function, then we try to subject it to some constraint. And this constraint is on the columns of set. Then how do we deal with a constraint optimization problem? The only technique that we've learned in Calculus 3 is by using Lagrange multiplier. And don't be too scared about using Lagrange multiplier in this occasion because Z transpose times Z equals to identity. If you spread that out, okay, this is really just a collection of many equations, okay, of scalar equation. So they are just a bunch of constraints. And that Z I transpose times Zj equals to delta ij. Delta ij means it's either equal to 1 or 0, depending on whether I equals to j. And the trick is that, okay, now we have many constraints. And in Calculus 3, you know that every time when you have an additional constraint, you need to introduce an additional Lagrange multiplier. So in this case, you need R squared Lagrange multiplier because they're R squared constraint, although some of them are repeated, it's fine. But the trick here is that instead of introducing a bunch of Lagrange multiplier, let me introduce a matrix of Lagrange multiplier. So I'm going to organize, okay, this Lagrange multiplier as a square matrix because I need R squared. I have R squared constraint here, so I have R squared Lagrange multiplier. And also because this constraint is called symmetric, because set I transpose set j equal delta is the same as set j transpose set I equal delta. So the Lagrange multiplier, the matrix of Lagrange multiplier, is also a symmetric matrix. So this is due to the symmetry of the constraint itself. So why do you do all this? Because now I can formulate my Lagrangian function, okay? I don't think in Calculus 3 we introduced Lagrangian function. But then Lagrangian function is just the objective function, the function that you want to optimize, minus lambda times your constraint. But then now, okay, now we're doing essentially the same thing. The function that we want to optimize is in the front. That is 1/2 times the norm, the Frobenius norm of A minus set x times set transpose square. And then I minus, okay, the Lagrange multiplier times, okay, the Lagrange multiplier is lambda. And then the constraint, okay, the constraint is given by set times set transpose, sorry, set transpose times set minus I identity. And I'm taking trace here just to make it scalar value. I'm putting a half there just for convenience later, okay? Actually, I don't need that half there. Later I'll figure out I don't need that half, okay? But anyway. And later on I discovered that the more official way to write this in economics is like this. Lambda, okay? Lambda is a variable as well. Sorry for the notational disaster. Okay. I'm going to simplify this expression a little bit. Okay, the way I simplify it is by introducing A minus x set transpose, this term in the middle. I call it R. Okay, I call it R. So what is the Frobenius norm? The Frobenius norm is really, sorry. Let me write down. What is the Frobenius norm of R is really the trace of R transpose times R. But I'm going to do a little trick here. Because last time I mentioned that as long as the multiplication is defined, then you can swap the two terms inside trace, okay? It will give you the same trace. So as a result, this is really 1/2 transpose, R transpose minus a half trace Lagrange multiplier, your constraint. So far, I didn't do any difficult mathematics, right? It's just organizing what you have done in Calculus 3, but in a matrix manner, because all the constraints are symmetric, and then literally F3, your objective function is also symmetric. Then now, what do we do? Now we have the Lagrangian, then we try to write down the so-called first order condition. So if you're unfamiliar with this term, it just means the derivative equals 0. So let me have a look, okay? So previously, we write down the Lagrangian like this. And then, what is the first order condition here? Is that when L is minimized, it turns out we must have x equal A times Z, okay? So let me give you a proof. Now something that is different here from previously is that this time we have three matrix variables here. Because there's x, there's Z, there's lambda. So I say add a lambda. I forget that stupid Lagrange multiplier. But all the examples that we've done on Wednesday, okay, only involve one matrix variable. But it's fine, okay, it's fine, okay, because now you grow up, you know that many variables and one variable are the same. For example, in Calculus 3, you may call this three variables function, but you can also say that this is a one variable function where x is in R3, okay? So in some way, okay, the number of variables is not very important. But the point is that I can focus on differentiating with respect to just one of the variables. For example, x, okay? So let me focus on consider partial differential with respect to x, okay? So when I say consider partial differential with respect to x, that means that you regard the other two variables as constant. Regard z and lambda as constant. And the partial differential with respect to x, I'm going to denote it by dx, okay? d sub x. But later on, when I get lazy, I may just click d, okay? Because I'm going to work with one of the variables only. So now let me have a look on the original Lagrangian. And then you look at the function on the right hand side, you realize that on the right hand side there are two terms here, the way, okay? And the second term has no x, okay? Because there are only lambda and z. So when you differentiate with respect to x, it's kind of disappear totally. So as a result, this becomes just half differential with respect to x trace R transpose. And then you continue, okay? You continue. And then using a technique that we developed last time, firstly, differential always commute with trace, okay? So this is really half trace and differentiated with respect to x, R transpose. Then this looks like something we've done before, so we leave that to you. You should check by using product rule, okay? And that's why I introduced that stupid 2 in the stupid 1 over 2 in the beginning, because when you compute the derivative correctly, there's a 2 appearing in the front, so they can't cancel. So you get just trace of R dr transpose. And last time I explained, okay, dr transpose. Oh, does it mean dr transpose or dr transpose? The answer is does not matter because they are the same, okay? And last but not least is that, what is R? Remember, day 1 R is A minus xz transpose. So R, okay, R is A minus xz transpose. And now if you transpose everything, then you get A transpose and then minus zx transpose. Okay. So as a result, dr transpose, because you differentiate it with respect to x only, so that is regarded as a constant, so you get minus z dx transpose. So as a result, this term can be transformed, become just minus trace, and then what is that stupid phone call? And something I'm going to do a little faster, okay, a little faster is check. Because at the end of the day, I want to make this become dx, so I need to transform and also use the commutativity of trace. So if you do it correctly, this turns out to be the trace minus our set transform dx. If you wish, you can put the minus inside as well. It's not very important. So using the standard technique about playing around with trace, okay, two things you transpose what is inside trace. Second is you can commute things, okay, as long as they defined. But the point is now you write in the standard form, so you can recognize what is the gradient. So the gradient of my Lagrangian with respect to x, okay, and then will equals to not the red box, but its transpose, so minus r times z. And last but not least is at a minimizer, that according to a generalization of result from calculus 1, then you know that, okay, in calculus 1, a minimizer definitive will be 0, and then in a more highbrow level, then it means the gradient must be 0. Of course, 0 means still matrix here. And what is R from day 1? R from day 1 is just a shorthand for A minus XZ transpose. So if you multiply that out, you get AZ minus XZ transpose Z equals 0. And this is a second occasion to witness that why your constraint is called convenient, because you impose a constraint such that the columns of set is orthonormal, or equivalently, this guy is the identity matrix. So that's why at a minimizer you get x equal AZ. Okay. So this is really coming from the first order condition. That the derivative at with respect to one of the matrix variable equals 0. Okay, so now we know that a minimizer, when you obtain factorization of a rank B matrix, okay, then it turns out X must be AZ. Okay, X must be AZ at a minimizer. And then what do I do next, okay? After that, let me try to simplify the original objective function. So originally, fxz equals to a half times the Frobenius norm of A minus xz transpose square. Okay. And then now I know that at a minimizer, according to the theorem we proved just now, at a minimizer x must be AZ. Minimizer, x must be AZ, So the objective function that will become f of az, comma z equals to half, okay, half, and then the Frobenius law of az z transpose, the f squared. And what I'm trying to claim is that it turns out you can simplify this term and then simplify it as just the half of difference of two traces. So let me just do one step and I will leave the rest for you. So Frobenius law of an ugly guy, of this ugly guy, is really just a trace of itself transpose times itself. So you didn't do anything intelligent. This is literally the definition of Frobenius law square. It's a trace of the matrix transpose times itself. Then, I don't want to do this algebra, in the public way, then nothing enlightening. So let me just say, a bit of brute force. Spell out the bracket, okay? Spell out everything. Then simplify. Then it turns out, then you're done. So it's really trace of AA transpose. So A transpose A, and minus trace of Z transpose A transpose AZ. Then nothing intelligent in the middle, okay? Just spell out that bracket and then use the fact that trace is linear, and then you realize that there are a lot of terms that will get cancelled. So there's nothing intelligent at all. But what's the point of doing this, okay? The point of doing this is that originally what we want to do is to minimize, okay? Minimize my objective function. I want to minimize this. But now, in this step, I recognize that this is really a constant of, A is given, so this is also a constant. Okay, this is also a constant. So this is equivalent to maximizing the term, the second term over here. So let me write down. So upshot is that to minimize f of az z subject to the constraint, which is z transpose z equals identity, it turns out it's equivalent to maximizing the trace of z transpose A transpose A z subject to the same constraint. Okay, because of this relation over here. To minimize this is equivalent to maximizing the second term. So this is the purpose of doing this ugly algebra, is to transform your question into minimizing what you want into maximizing a certain trace, okay? I don't know whether you're sensitive enough, okay? Whenever you see A transpose A, either it will trigger some of your memory or trigger your PTSD, because we've seen this matrix a lot of times before the midterm. So we mark, or we call, a matrix, a symmetric matrix, is, okay, positive semi-definite if and only if B can be written as A transpose A for some A. C, midterm. Of course, in the midterm, I didn't say positive semi-definite. I say all the eigenvalues are real and non-negative for it, which are the same thing. And you have done that in your homework a couple of times as well. So in other words, okay, now we transform the original question about minimizing the objective function into maximizing trace set transpose as positive semi-definite matrix here, subject to certain constraint. And it turns out this is a solved question, a very classical result. So let me just cite it. The proof is also not very difficult. So this is where linear algebra will come in, okay? Because I don't know how to prove this by using calculus, to be honest. So it turns out when you have a positive semi-definite matrix, and then because it's symmetric, so all the eigenvalues are real, and also because it's positive semi-definite, so all the eigenvalues are greater than or equal to 0. Then the question is, what is the maximum value of the trace of set transpose B set subject to the constraint that we studied just now? And it turns out the maximum value is given by the sum of the R largest eigenvalues. So it's a sum of R largest eigenvalues of this symmetric matrix B. And moreover, this will also tell you when this maximum value can be attained. This maximum value is attained when the column of set is formed by the eigenvectors correspond to those R largest eigenvalues. It turns out we transform the original problem into a very classical problem solved by Radon. The proof of this I will postpone it later, okay? But let me use this result directly to deduce, okay, the lower rank approximation theorem. So the lower rank approximation theorem, okay, I try to minimize my objective function that I stated in the beginning, but then now I transform it into an equivalent problem about maximizing the trace of set transpose B set. And then how do I obtain the lower rank approximation theorem? The way to do it is first you start with an S3D of the given matrix A. Then we know that A transpose A is the symmetric matrix, and every symmetric matrix can be orthogonally diagonalized, and because the S3D is U sigma phi transpose, so A transpose A can be orthogonally diagonalized by V. And of course, you note this from the midterm, you know that this matrix A transpose A is positive semi-definite. So let me let its eigenvalues to be lambda 1 up to lambda n. And it's positive semi-definite, so they are all greater than or equal to 0, so be eigenvalues of A. And then every eigenvalue has a corresponding eigenvector, so let V1 up to Vn be of a normal basis of eigenvectors of A, and then such that V1 should be an eigenvector of lambda 1 and so on, so AVI equals to lambda IVI. And then now we just apply directly the linear algebra theorem that I stated above, the Rayleigh theorem. So by using the Rayleigh theorem, then what is the maximum value? The maximum value of the trace, of Z transpose and then A transpose, AZ, is given by the sum of the R largest eigenvalue. Not eigenvalue to A, eigenvalue A transpose A, Jesus. A transpose A. Sorry, A transpose A is plus example different. Not A is that. A is not even a square matrix. But lambda 1, lambda 2, up to lambda R. The R largest eigenvalue, the sum of R largest eigenvalues of A transpose A. Then now you're essentially done because, what is the relation between singular values of A and eigenvalues of A transpose A? It is eigenvalues, they are square of the singular values. So it's sigma 1 square, sigma 2 square, and sigma R square. And then where sigma I are the singular values of the original matrix A. So this is a theorem we proved a long time ago with the relation between the singular values of a matrix and the eigenvalues of A transpose A. And moreover, according to the same theorem, this maximum value is attained when you take Z to be formed by the R largest eigenvectors, So this is attained when Z is formed by the columns of eigenvector corresponding to the R largest eigenvalues of A transpose A. So in other words, it would be V1, V2, or VR. But once upon a time, when we learn SVD, we give this matrix a name. We call it 3R. So this is the first R columns of the matrix 3. So it's like you try to truncate your matrix 3 by just leaving the first R columns. So, what is B? Remember, B from day one, B is XZ transpose. XZ transpose. And then now we figure out what is Z. Z is VR. We figure out Z is VR. And also, what is X? X is AZ. AVR. So, from the two sets combined together, we know all the information. So we know what is Z, and also what is X. X is AZ. And we can simplify it further. Why? Because I know the SVD or SVD of A is given by U times sigma times 3, and then you have VR and the VR transpose. Sorry, there is a transpose here. And then if you're good at doing matrix multiplication, these two terms. Because the point is phi is an orthogonal matrix, okay? So all the rows or columns are orthogonal to each other. So when you compute phi transpose times phi r, then you will get something that almost looks like identity. But you don't get a square matrix, okay? So that's why it's not exactly identity, but looks like a truncated identity matrix. And finally, let me combine these two terms in the middle. So these two terms in the middle, if you do matrix multiplication, then you get, let me call it sigma r 0. So I'm not doing anything advanced, I'm just doing matrix multiplication. And then what is sigma r? It's just this matrix formed by, it's a diagonal matrix formed by the first of singular values. Well, when you multiply by something that looks like identity and then with 0, block multiplication tell you that only the first block will survive. Then you're done, okay? Because spell this out. If you really spell out the matrix multiplication here, then you will get a sum, and then you get this singular value, sigma I, and then you get ui, and then vi transpose. So a product of a lot of rank 1 matrix, okay? But not all of them, only from I from equal to 1 to R only. And then what is this? This is exactly what I call truncated SVD in week 9, okay? Which is the truncated SVD in week 9. So that's why the matrix that can help you to approximate the original matrix as best as possible with respect to the forbiddance law is B, and B is the truncated SVD. Okay, so this is a new proof of the old result, but then using calculus. But saying that using calculus is not totally honest, because in the middle we have, I can't avoid myself using some linear algebra input. So in the last 5 minutes, I just briefly explained, okay, how this theorem by Raymond can be proved. So I've typed it already. Okay. So you try to minimize, okay, to maximize, okay, you try to maximize the trace of set transpose BZ and subject to set transpose set equal identity, but B is not random. B in the beginning is positive semi-definite symmetric matrix. So in particular, symmetric, so we can start with our OMB of eigenvectors of this matrix B. I call it phi1 of the phi n. And the proof is not, to be honest, it's not that intelligent. I mean, I don't get a very intelligent proof. I just spell out everything. So in the sense that, okay, I want to maximize, okay, trace of set transpose B set. So let me write that out. And then as terms, as a scalar term, then how do I do that? Firstly, I call the columns of set to be set 1 up to set R. And because I have a basis here, I have an OMB here, so every set can be written as a linear combination of the Phi. And then after a few brutal expansion, the function, the objective function that I want to optimize, turns out can be written in a scalar. Okay, sum lambda 1, gamma 1, lambda 1 are the eigenvalues, okay, are the eigenvalues of B. And how about gamma I? Gamma I is just a shorthand of the sum of alpha ij squared. What is the alpha ij? Alpha ij are the coefficient when you express, okay, set J is a linear combination of the phase, okay? So I firstly rewrite the function that I want to optimize as a sum of this gamma I. Then I discover there are two constraints on gamma I. Firstly, when I sum all the gamma I, that I get R. So this is the first condition that I realize, okay, the sum of all this gamma turns out to be R. The second thing is that by using, this is not a difficult argument, but then you can recognize that gamma I turns out is a projection, because it looks like some kind of projection. So it turns out when you project, okay, the length would be so this is the projection of Vi. But previously we know when you project, you make the original input smaller, the length of which smaller. But this is an OMB, so this is at most 1. So that's why gamma I is at most 1. And obviously gamma I is non-negative because it's sum of square. So as a result, you reduce, okay, your original optimization problem about maximizing the trace of set transform B set into a ridiculous problem, okay? That is to maximize this guy. And now you have two conditions. Condition number one is the sum of all these gamma I is R. And this turns out all these gamma I are between 0 and 1. Like if you don't know how to do it, it's just because the symbol looks a bit confusing. But then think about toy question. If I ask you to maximize 7A, 6B, 5C, and now you have two conditions, okay? Subject to all these ABC are between 0 and 1, and then A plus B plus C equals to 2. Then how are you going to optimize it? Of course, you will give all the available numbers, okay, to A and B. So this is not intelligent optimization problem, okay? It looks intelligent here, but then when you write our example, this is extremely stupid, okay? It's achieved when A equal B equal 1 and C equals 0. So analogously, okay, here, when you obtain the maximum value is exactly when you allocate all the variables to our largest gamma. So when all the gamma, first our gamma is 1, and the remaining are 0. So that's why the maximum value is lambda 1 up to lambda R. And then this is attained when set equal to V1 up to VR, because what is set in the beginning is there's a relation between set and Vi. But now you're choosing the kind of the extreme case, okay? So this is done. So it's not a very difficult proof. You just spell it out and realize that you can reduce it to a toy question. And I got something very quirky at the end to say, okay? The quirky thing that I want to say at the end is that, not to my knowledge, okay, I spent a few weeks to do it, and it seems that it's difficult to me. If you can do it, okay, with just doing calculus, let me know, okay? But it seems difficult to me to derive the low-rank approximation theorem by just using calculus. So it looks like some genuine linear algebra input is necessary. For example, when I prove the radiance theorem, I use the spectrum theorem, okay? So there's a genuine linear algebra input. So that's why learning calculus is not enough. So it's fair to say linear algebra wins, okay? And then, so that's it, okay? So I will finish my course here. And then good luck to your examination next week, okay?